Okay, thanks, Justin. Hello, my name is Philip Bangerter, your moderator for the session. I live and work on the lands of the Turrbal and Jagera peoples, traditional custodians of the lands and waters of the Brisbane area. I take pleasure in acknowledging their traditional custodianship of the land and pay my respects to ancestors and their descendants who continue cultural and spiritual connections to country, as well as making valuable contributions to wider society. I also declare my support for the Voice to Parliament and of the Uluru Statement. I wish to convey similar sentiments to the Haudenosaunee and Anishinaabe, the Canadian First Nations peoples who hold traditional connections to the land on which Brock University is situated. Welcome to you all for this exciting session of the LIAMforum. I did not know Liam Zisman, but I've heard much about him from his father, Azil. Liam perhaps typifies the young professional that the geosciences and indeed the mining industry should attract. Passionate and caring, smart and wanting to make a difference. The assembled panel today wants to talk about it in terms of challenges, but also the exciting work going on in applied research on several topics. I'll be asking each of them to self-introduce at the start of their contribution, which will run for a few slides in the area of expertise and their current focus. As we progress through each panelist, we would love it if you could drop a few questions into the Q&A chat facility. Our Brock Tech support will assemble the questions ready for us after the panelists have offered us their wisdom. So we have a current mining company executive to start us off, followed by that rich tapestry of all that exciting initiatives at Canadian universities to learn about. So without any further delay, I'll ask Philippa to start the ball rolling, if you wouldn't mind.
Thanks, Philip. So to be a sustainability practitioner does bring great challenges, but for those of us with the will and the passion to champion transformation, it also brings great rewards. And as you can see from this slide, the resources sector has no shortage of challenges. But the backdrop of dissonance, and think of that as a fancy word for discord or dissatisfaction, is exactly the platform that we need to drive the sector's next transformation. So as Philip said, I'm Philippa, and I've been a sustainability practitioner in the mining industry for almost 30 years. My current role is as Head of Sustainability for Horizonte Minerals, which is a mid-tier nickel development company. And at Horizonte, we're actually on the dawn of our own transformation from nickel developer to major nickel producer. We have one tier 1 operation, which is under construction, Araguaia, which is in the Pará state of Brazil. And we have our second project, which is about to move into feasibility study, Vermelho, which is also in Pará state in Brazil. And I'm quite new to Horizonte, so what I'm going to reflect on today is my perception of a company that I've recently joined and the journey that they've been on already towards leadership in sustainability. We have with this company a great example of an organisation with a strategy of integrated sustainability. And I'm going to highlight our approach to this with a couple of key examples. One of the things the industry is challenged with most today is relevance. And nickel has never been more relevant than it is today. Geothermal power stations, wind turbines, hydroelectric plants, nuclear power stations, electric batteries, even carbon capture and storage are not possible without nickel. For Horizonte, though, it's not enough to be part of the supply chain for a critical mineral. It's our goal to provide community leadership and industry differentiation. As an example, biodiversity is inherently linked to conservation and forest protection. And as we all know, therefore connected to climate change mitigation, and also adaptation and resilience. Within Horizonte, since 2013, we've been conducting detailed biodiversity-related studies to global best practice standards, and we've developed a detailed biodiversity action plan that we're implementing at our Araguaia operation to ensure a net positive impact to biodiversity. But what I particularly want to point out today, related to our theme, is, and it's the image you can see on the right-hand side, Metallophilus savanna, or kanga, as it's colloquially known, is a type of critical habitat, and it's home to floral species that are new to science. And importantly, it's through research into these kanga habitats or biomes that we're learning about metal homeostasis, metal metabolism, and the role that metallophytes may play in bioremediation of metal contaminated sites. So we have here an example of biogeochemistry in action, which links directly to what some of my colleagues are going to discuss in their presentations. Imagine an environment where we could speed up mine site reclamation because we understand the biogeochemical processes that occur within soils. This is of critical importance because as we're creating man-made structures post-mining or in the course of mining, how do we then recreate climax communities in a much shorter space of time than they were created in the natural evolutionary environment? Another example for Horizonte, and a key component of our mission, is to reduce our carbon footprint. One of the earliest components of our value engineering for Araguaia was to explore the opportunities to reduce the emission intensity of our operation. Key opportunities have been identified in the design of the processing plant, in the operations, fuel substitution opportunities, renewable power, and also offsets. And all of these in combination have the potential to allow Araguaia to evolve to having a carbon footprint which is in the lowest quartile of our peer group. And that's what this graph shows here. You can see Araguaia's baseline with no improvements, and where we're able to drive ourselves, which is the green bar, with the implementation of all of the opportunities that we've identified. But our work here is not complete, and we continue to explore other opportunities. And some of the most exciting opportunities are enhanced weathering and accelerated afforestation. And again, these rely heavily on biogeochemistry and are emerging opportunities that will be discussed by our other colleagues on this panel. So just two examples for today, but these programs are just a fraction of Horizonte's wider strategic approach to sustainability. Some of the other key components are shown here and are discussed in more detail in our sustainability reports for anyone who's interested. But significantly, and what I find most impressive about all of the work that Horizonte has achieved as a relative newcomer to the organisation, is that all of this extensive planning, research and preparation was completed before we turned a single sod of soil. Our groundbreaking activities commenced at Araguaia in May of this year, and all of the work that I've discussed today predated this.
Thank you very much, Philippa. Excellent timing as well. So very pleased to hear about the early work there. I noticed your comment around carbon there. For anybody who's listening that has an interest in carbon modelling, particularly in the mine planning arena, then I could recommend session 4B tomorrow as a place to look for some more there. I'm going to move it on now. Sasha is next.
So I'm a professor at the University of Alberta in Edmonton, Canada, and I work on CO2 sequestration by enhanced weathering and looking at ways to use bugs and water to extract more of the critical metals we need for the clean energy transition from rocks. Next slide, please. As Philippa introduced, we need more. We find ourselves in a situation where we need to build a net zero carbon economy, and we need all of our energy infrastructure to be carbon neutral very soon. we find ourselves in the bind that we need more mining to build this infrastructure, to extract the critical metals we need to build the clean economy. The International Energy Agency predicts that some of the metals we need, including nickel and cobalt, which are needed for batteries, we need a supply that's between 6 and more than 20 times what we're mining today by 2040 in order to decarbonize our energy systems. So while we're extracting more critical metals, we also need to do this from carbon neutral mines. So mines that don't emit any net carbon dioxide to the atmosphere. So this is a profound challenge, and we need expertise from new scientists and engineers and social scientists to meet these goals. I'd like to talk about some of the work my lab has been doing in this space today. Next click, please. So there's a synergy between mining and removal of carbon dioxide from the atmosphere to store it. So in this slide, what we see are a variety of technologies that have been developed for removing carbon dioxide from the atmosphere to help us reach net zero by 2050. And so some of these are very familiar, such as afforestation or reforestation, planting trees to trap carbon dioxide from the atmosphere into woody biomass, regulating soil carbon in agriculture. And some of them are quite technological, for instance, direct air capture in the middle, where we have fans that suck carbon dioxide out of the air and absorb it, where it can be pumped underground into rocks for permanent storage. Where we have a synergy with mining is in a strategy called accelerated chemical weathering or enhanced weathering, which basically just means dissolving rocks faster. Next click, please. And so that's what I'm going to talk about today. Oh, and if you could go back one, that would be great. Thanks, Virginia. And perfect. And so it turns out that Canada is one of the world's biggest producers of nickel, which we need for energy storage in batteries for electric vehicles, and also for storage of renewable energy. So the sun doesn't always shine, the wind doesn't always blow. So if we're using solar and wind power, we need a place to store it. And we need nickel for batteries. And so most of the rocks in Canada that host nickel are magnesium silicate rocks, and those are the absolute best rocks for trapping carbon dioxide from air. One interesting thing about nickel deposits in Canada is that the nickel is found in 3 different types of minerals: alloys, sulfides, and magnesium silicate minerals. Our ore processing circuits for Canadian nickel mines can recover nickel from sulfides and alloys, but they miss the 30 to 50% of the nickel in any mine that's stuck in these magnesium silicate minerals, that green mineral in that picture. So there's an opportunity to use carbon sequestration techniques to recover that extra nickel that we're throwing out today. Next slide, please. So I've got a chemical equation on here for people who like chemistry. So those magnesium and silicon-rich green minerals in the top left also contain a lot of iron and nickel, the nickel we need for batteries. And fizzy water, rainwater, naturally dissolves these rocks. So when carbon dioxide dissolves into rainwater, it makes an acid. And so if you've ever mixed baking soda with vinegar for fun, it bubbles up. It's a neutralization reaction that creates new products. That's exactly what we've got here. Rainwater dissolves these basic magnesium, iron, and nickel silicate rocks to make, on the bottom, hydrated silica. When you buy electronics, it's that sachet that says "do not eat" that keeps your electronics dry. And it also makes magnesium carbonate. And that permanently binds the carbon dioxide that was in the atmosphere into a rock. Magnesium carbonate is what we eat for antacid, or if there are any rock climbers, it's rock climbing chalk that you use to dry your hands. And the last product is rust. So just like rust you get on the bottom of a car or a bicycle. And so where the magnesium carbonate traps all the carbon dioxide, the rust traps all the nickel. And in nature, all the stuff gets mixed together, so you can't get the nickel out. So there's an opportunity to use this reaction that sequesters CO2 as an ore processing technology too. Next slide, please. And so my co-workers and I, particularly Jess Hamilton, who's a staff scientist at the Australian Synchrotron in Melbourne, We went out into the field and we did a several ton experiment to see whether we could separate the magnesium to bind carbon dioxide and the nickel and rust so that we could recover all that 30 to 50% of the nickel in this mine here, the Woods Reef mine, that had just been thrown out. And so this is in northern New South Wales in Australia. And in the left corner, the right corner, you can see two 1-ton tanks. One has creek water that we laboriously hauled up a mountain of mineral wastes using a garden trailer. And the other has a dilute tank of acid. And we used a slightly more awesome acid, sulfuric acid, because it's something that microbes naturally make in mines. And so we had a solar-powered sprinkler system that sprayed either water or this dilute sulfuric acid onto these magnesium, iron, and nickel-bearing minerals. Next clip, please. What we found was that a layer of rust, just as we predicted, formed right away. So in the image on the left-hand side, you can see a layer of rust. It's orange and red. And we suspected that was concentrating nickel along with the iron, which we know is in rust. Over the course of several weeks, where we had more additions of these acid treatments to dissolve the rocks in this neutralization reaction, that layer of rust became thicker and darker, and it got pushed down several centimeters as we leached all the good stuff, the magnesium and iron and nickel, out of the rock. And so in the image on the bottom right, you can see a thick rusty layer in a hole that we dug through the surface. Next slide, please. Thanks. Now, when we cut a little section out of that, and we took it for a chemical analysis at a big research facility, a synchrotron light source, what it lets us do is map exactly how much iron, cobalt, nickel, other metals there are in a slice through that acid-treated section. And in the top left, you can see we've got at the very top of those diagrams at 0 centimeters depth where the acid was poured, and on the bottom, about 6 or 7 centimeters depth, where a magnesium-rich water came out that we could use to bind carbon. In the middle, highlighted in a box, we've got brightly colored spots in that leftmost bit. That's a map of iron concentration. So where the colors are hot, there's a lot of iron. Where the colors are cool, there's less. And so that's our rust layer, the red rust layer that we can see in the bottom right. And in a map of chromium concentration, cobalt, nickel, and manganese, we see all those metals are associated with the rust, just as we expected. We managed to concentrate nickel from about 0.1% to about 1%, which is pretty good. And we leached 80 to 90% of it out of the rock with this acid treatment, recovering the nickel from all the minerals, including the silicates, which haven't been able to process previously. Next slide, please. So the nice thing about this process is we're making something like a nickel-rich soil, which is what nickel is hosted in South America. For instance, in the mines Philippa was talking about. So we already know how to process that. So it's a new way to recover nickel, as well as making CO2 sequestration possible. So because this session includes bugs, I wanted to talk about how we can use bugs to finish this process. Those green slimy ponds there are 1.5 ton tanks of pond slime. This is these are photosynthetic microbes that were cultured from a mine. And what we did was we fed them our magnesium-rich waters that we got from pouring solutions over these highly reactive magnesium silicate minerals, mine residues. And we feed that magnesium and sometimes calcium-rich water to the bugs. And over the course of several months, these microbes pull carbon dioxide out of the air and bind it with those metals that are in water. And you can see on the left side is an image of a lot of gross goo in a shovel. That is calcium and magnesium carbonate minerals in a sediment that's several centimeters thick that was made after 6 months of just sitting with these microbes. And those are that's the same type of rock that's being made that stores carbon dioxide in the Rocky Mountains, and it's what the Niagara Escarpment in southern Ontario is made of. So all of this was designed just by having a think about how rocks dissolve in nature and how microbes help sequester carbon dioxide. And so there's a lot we can learn from natural processes that we can implement in ore processing.
Okay, thank you, Sasha. That is absolutely fascinating. I suspect that you and I might be able to have a conversation offline about some of that. Excellent. I might add that mine in northern New South Wales is in driving distance of my house, so that would be terrific. All right, I'm going to, and thank you for keeping to time too.
Thanks so much for the invitation to participate in this forum. It's extraordinary to be able to share my career experience as well as what I'm doing right now as a researcher. I'm a geologist with a PhD in environmental science, and currently I'm a postdoc in Dr. Ian Power's lab at Trent University, where I conduct research in mine waste used for carbon sequestration. I collaborate with Sasha, so you're going to see some overlapping in what I'm saying here. And why carbon removal? I want to share some of what is the motivation behind using mine wastes as a resource for carbon sequestration. We are currently at a point that to be able to maintain the increase of temperature of our planet below 2 degrees, we need to rely also on new technologies, negative emission technologies. That's what they call, that will enable us to remove CO2 from the atmosphere. The atmosphere is acting as a bathtub. It's almost full. If we don't open the valve and remove some of that CO2, we're going to see our planet temperature increasing over and over. The problem with the negative emissions is that we currently don't have the technologies developed or the capacity to remove the amount of CO2 needed to fulfill our objectives by 2050. So it is estimated that we have to increase from less than 0.1 gigatons removal per year into 10 gigatons per year. This is an enormous effort that needs to be done, and is creating this lively ecosystem of partnership between research and industry to develop new technologies, as Sasha has showed in her slides. In our case at Trent University, we are focusing our research on enhanced weathering, which by definition consists on spreading pulverized rocks onto soil and into the ocean to enhance the natural rock weathering processes and consume CO2. So as scientists, we study the carbon cycle. We study the reactions that happen between the atmosphere, the rocks, and the waters. And what we know from that is the chemical reactions. The CO2 with rainfall reaches land, weathers rocks, which then will keep the CO2 in the waters, and that then flow to the ocean, and eventually they will sink as carbonates there. We know that in the process, we have also microbes in the soils and microbes in waters that they can accelerate these processes. They can accelerate the dissolution of the rocks, but they can also accelerate the formation of rocks. So bioweathering or biomineralization. So we study all these processes, and then we try to integrate them into solutions for carbon sequestration. But enhanced weathering relies heavily on using rocks. And what other industry has access to rocks, either by creating new mines that will be mined specifically to produce rocks for carbon sequestration, or, as I prefer to see it, why not thinking about a more integrated approach to this and use more the mine waste is in a more conceptual way of circular economy. So mine wastes are equal to pulverized rock. And just to give you briefly an example what we do, so in terms of enhanced rock weathering, we go to these sites, to the tailings, we collect samples, we analyze, we use sensors, water chemistry, geochemistry, and different proxies to quantify how the amount of atmospheric carbon dioxide that is being sequestered by mine tailings. We also run experiments in the lab where at different scales. For example, we look at what happens at the mineral surface, what transformations happen there when reacting with CO2, and then we also develop methodologies to quantify the carbon dioxide sequestration. So ultimately, what we're defining with these studies that we do on site and in the lab is the baseline of how much mine tailings are sequestering, absorbing from the atmosphere. And eventually, we are developing tools for validation and reporting of carbon sequestration, which will be extremely important in this transition to carbon neutral mines to validate and offsets, or even and which are extremely important for in the context of carbon markets. But we also want to accelerate the rates of a co-benefit of also using this technique could be cementing tailings. And here in this photograph of a electronic microscope, you see a piece of tailings here, the grains of tailings, and in between, I highlighted in red, these fine-grained carbonate cements that were originated by the reaction of the microbial CO2 with the minerals in the tailings, and now are agglomerating this. So there are several advantages of thinking about natural processes and integrating into mine wastes. One of the major advantages is that they're cheaper, they require less energy, but also have co-benefits, which could be formation of soil for reclamation and cementation of tailings for stabilization. And these are just examples of research we do in collaboration with the industry, and that are leading the next steps of sustainable technologies for mine waste management. Thank you.
Fantastic. Thank you, Carlos. Also fascinating. I suspect I might have to have a conversation with you as well offline. Terrific. I'm personally very interested in tailings, and it's several links there. All right, now finally, Leslie, if you wouldn't mind sharing, and it's your turn.
Perfect. Thank you so much. And thank you to Sasha and Carlos for setting me up so perfectly. One of the issues that goes along with mining being central to the energy transition and the need for more mining is, what do we do about all the water that they're using already? How do we improve stewardship? Because if we're going to need more mining and then they use more water, we're in even more trouble. And one of the worst things we can do is come up with climate change mitigating solutions that then irrevocably wreck our water supplies. We are working with the mining industry to look at more effective and smart solutions using endemic microbes present in their waste streams as strategies for not just monitoring and mitigation, but potentially treatment. What I'm showing you on the slide here is a tailings discharge coming into a tailings impoundment in Northern Ontario. And then there's a blow up of the particle. You can see this little purple and red particle, and that's a pyrrhotite or an iron sulfide tailings particle. It is entirely coated with bacteria. Those bacteria are largely undiscovered and undescribed. We know that bacteria or microbes are present in almost every environmental context you want to examine. They're not just there, they're interactive with those contexts. And this is the field of microbiome science, which is starting to think about, now that we have the tools, how do we use those tools to understand what these invisible engineers are doing? And so this idea of a microbiome is a complex microbial community. So if we go to your interior gut, if we look at the built environment, every time you touch a door handle, if you think about the planet, if you think about soils or the oceans, there will be a complex community of microbes who are doing differing kinds of metabolic functions within that context. They shape the context, and they are themselves influenced by the context, and they're distinct. So we have seen that the research that's occurring in these contexts has exploded over the last 20 years, and it's really provided transformative new insights. And in fact, if you look at COVID vaccines and the platforms that are being developed, that comes from these molecular biological tools that have been developed and are being enabled. And so the resolution that's enabled by the rapidly developing technologies and the fact that the prices have come down exponentially means that we're not just going out and doing sort of an arbitrary, let's have a look at what bacteria might be present in a system. We can actually interrogate, what are they doing and how are they doing it? What are the outcomes? What are the controls? And if we accept the premise that mining wastes and wastewaters are actually biologically reactive contexts, then this makes all kinds of sense about why we might want to do that. And as I said, we're asking fundamental questions, you know, and I think this is something that we're seeing in this particular area. It's such a fascinating area where we're looking at fundamental, advanced, interdisciplinary research in very applied contexts that are really trying to tackle these grand challenges. But we're asking these questions. Who's there? What are they doing? How do they do it? and what are their controls and their outcomes. And one of the things, and this is a recent book chapter that'll be coming out this year, one of the things that's very obvious when you look at all of the sequence data, so sequences are essentially the DNA coding, the playbooks for all of these different kinds of environments that researchers are finding, whether it's, as I say, the human gut or the deep oceans. Those sequence information on the bacteria are typically provided through national publicly available databases. So the NCBI is one of the biggest ones. If you look at mining systems, those investigations represent less than 0.2% of all of the projects to date. So mining systems are essentially microbial black boxes. They have not been well studied, and they represent low-hanging fruit. So we started a project about 5 years ago, working with multiple mines, an international and multidisciplinary team, to start addressing, in fact, one of the most recalcitrant and persistent issues that a number of mines around the world have been facing, which is sulfur compounds. So over 70% of the world's metals come from sulfide-containing ores. And so sulfur is widely present across the global mining landscape. It is ubiquitous, it is present in high concentrations, and sulfur, for anyone who's got a biology background, knows that it's one of the key biogeochemical cycles that drives planetary function and conditions. Sulfur is complex. It can occur in many different forms. We know that not all of those forms currently we can analyze for. Mines don't actually have detection limits for a lot of them. They don't have methods to monitor. We know that some of the compounds that occur actually go through their treatment, so they end up in receiving environments. The issue is that these sulfur compounds are reactive, and particularly under microbial catalysis. And bugs that like cycling sulfur can lead to acidity, toxicity, pH depression, oxygen consumption, fish kills. So if you can't manage and monitor and treat these compounds effectively, it's a risk to the environment and it's a risk to the industry. And it's a broad, widespread issue. So that problem catalyzed essentially an industry partnership, as I mentioned, with 3 mines, Hudbay, Sudbury INO, and Rambler in Canada, to really start tackling what the Canadian industry commonly refers to as the thiosalts issue. And within the industry, there had been a 30-year-long thiosalt consortium that had been trying to figure out why they couldn't predict this, why they couldn't manage it properly, and what they could do to improve that. And when we came in 5 years ago, it was very clear that the currently available methods were not effective. They were static, so companies were relying on chemicals and energy and infrastructure, which is not particularly sustainable, and they lacked fundamental mechanistic understanding of the processes and the compounds involved. And again, if you're only ever dealing with symptoms, you never tackle the root cause, then you don't ever get to a place where you have sound baselines that allow you to do things in a smarter way. So the MWS project, the Mining Wastewater Solutions project, came in to tackle root causes. And by that, it was taking an advanced look at what are the bugs in these systems, whether we're looking at the tailings ponds or the receiving environment, who's there, what are they doing, what are the sulfur compounds, how does that collectively result in the water quality issues that mines were seeing. We did this across a number of mines and their receivers that differ in their ore body types, that differ in their age and stage, so that the results were going to be from these 4 mines with the goal that they would be widely relevant to a broader set of mines. And obviously that the outcomes would really drive applied practical solutions, smarter tools that could take advantage of new understanding and new opportunities to use this biologically informed new knowledge discovery. And all of that is about helping mines achieve water stewardship, use less water, be efficient in the water they use, and ensure that the water they return to receivers is not going to cause problems down the road. And so when you take that sort of biosystems approach where you start looking at and I hope anyone who works on a mine or even just walks outdoors and looks at a soil or a puddle or your door handle now starts to realize that there are a whole bunch of biogeochemical reactions going on there. And so when we want to investigate those kinds of processes in a systems approach, we need to start thinking in 4 dimensions. We need to think about spatial differences. The top of the tailings pond versus the bottom is likely going to be very different in the reactions that occur. Similarly, over seasons, we need to think about what happens particularly in Canada, we think about summer versus winter, slightly different in terms of what you might see going outside. So we need to integrate these facets. So geochemistry, molecular microbiology, physicochemistry, environmental characteristics. And so we do this with a heavy tool belt. We do field and lab work. We're integrating across all of these disciplines with the goal that you start understanding fundamental process. And, you know, in 5 years, I'm very proud to say, you know, and this is a massive team and it's being driven largely by the young people, the HQP, highly qualified personnel that we have in our labs that are driving these knowledge discoveries. And in 5 years, we've already put new tools not only into development, but we've now got them actually in play at our mines. And in fact, Hudbay Minerals has gotten regulatory approval from their regulator to use our new sulfur mass balance method for their compliance reporting. They're the first mine in the world to do this. That method not only is more effective, cost effective, it's more robust in terms of predicting risk, and it's cheaper. So it's win-win all around. The mine is actually more effective at being able to adaptively manage because it can get real-time information, and we're able to use that to power down in terms of how research can keep driving novel technologies. In terms of the microbial takeaways, and unfortunately I don't have the time to walk you through all of the exciting results, but just to give you the takeaway, and if you hear nothing else, hear that bugs will be part of your solutions if you're a smart mine practitioner. The top takeaways that we see is that there is no question there is a distinct group of microbes in these mining systems that we don't see in any other system. So if you go and look in deep oceans or soils or other contexts that might be processing sulfur, they're not the same bugs. So they're a distinct mining group of sulfur bugs, and they're the same bugs across all of our mines. So this starts to speak to a broad set of mining sulfur cycling bugs that we're finding in Canada that are likely present in mines in South America or Australia. Secondly, we know that we can classify these bugs through understanding what they're doing metabolically with those sulfur compounds in terms of fast or slow. How quickly are they turning those sulfur compounds into sulfate and acidity? And we know that from a whole bunch of fancy bioinformatics and metagenomics and RNA work. More importantly, we also know what controls whether we have fast or slow bugs. So now you can see we're starting to build the chain. We're starting to see what are the reactive compounds that occur, the bugs that are catalyzing what reactions occur with those sulfur compounds, and therefore the outcomes, the levers, the controls on whether or not we get fast or slow. So now we start to have predictive sequences that allow us to essentially manage in light of new knowledge discoveries, but also what we're seeing on site in tailings ponds is predicting whether or not mines fail toxicity tests off site. And so that starts to be very important because our microbial indicators are actually more sensitive in predicting those compliance failures. A lot of mines fail toxicity tests that they have no explanation for why based on their chemical data. I think all of this really speaks to the power. You know, we're seeing this, as I've mentioned, in almost every other sector where genomics is being applied to develop smarter, more sustainable strategies. Not only will we be more effective in environmental stewardship, we decrease risk and liability for the industry. So the business case is obviously there. And what I would say to the young people is that we're, as we look at these water issues and climate change and sustainable development, first responders run towards the challenge. This is the industry that will pivot, I think, the entire world in terms of can we actually achieve sustainable development. Mining sits in the center. So we need to get its equation right, and we need smart, wide-ranging expertise and people willing to fight environment and climate change challenges through this industry. So thank you very much for listening, and I look forward very much to the conversation.
Okay, fantastic. Thank you, Leslie. Also fascinating, and I'm reminded of the term biomimicry through all of these talks, and the notion that nature provides us with pointers towards solutions and even solutions themselves. We have a few minutes. Justin's given us the warning on time, but we absolutely have an audience question which I'd like to explore. I'll read it to you. What do you figure is the tapped potential of using bugs and organisms to perform these tasks in the industry? Is it common method or largely a new frontier? I believe students may be inspired by this science. Well, I agree with the inspiration comment there. I'm not sure which of you would like to take that. Philippa, can I just point that at you and just give me a feeling? Give me a feeling of your knowledge or what you think a traditional mining executive or mining technical person might have of these sorts of things. And yes,
well, I think, as we've heard today, there's definitely some elements about this that are cutting edge and incredibly innovative, and we've got some great examples of where research and the industry are coming together to provide or to work on real solutions. But this is by no means widespread as yet, and I think there is plenty of potential. We only need to look at the fact that there's thousands of tailings storage facilities sitting out there today that we've not even started to explore to look at these opportunities for. You know, so I think whilst we've got a team here who can show some real life examples, there's a lot of potential to you know, really move this forward and make this something that, and as we heard today, I think that there's multiple solutions that can come out of work of this type. You know, carbon sequestration, the ability to enhance the stability of mine waste piles, the opportunities for enhancing afforestation. You know, this is just the tip of the iceberg.
I agree. When I'm giving away my age here, but I was at university in the late 70s and early 80s, and I got to say, and as a process engineer, we were concerned with efficiencies around the extraction of metals from minerals, and that continues. But there was little, if any, connection to other disciplines, if you like, in this area, and the you know, we've got a set of systemic problems, and you'll only get to solutions if you take a systems approach. Anybody else from the universities want to make a comment about the commonality? You're right at the front here, the forefront of this, and we've heard that you're connected with several mines, but do you think it's a bit more widespread, the knowledge of this?
I'll jump in quickly, Philip. I think that it's absolutely on the cusp. I would definitely say over the last, particularly 3 years, there's just, particularly in Canadian context, but I think more globally, the industry is suddenly cottoned on to the fact that genomics is low-hanging fruit, and it expands across, exactly as Philip has said. You know, bugs, like life of any kind, need carbon and energy source. What's interesting about microbes is that they can get that energy source from a variety of things. So from metals, from rocks, from water. There's a variety of ways they do that, which is why almost every aspect of efficiency or challenge in the industry, there likely is a smarter microbial solution that you could bring to play. And I think that, you know, what you're seeing here in terms of fundamental biogeochemical frameworks are being applied in earth science more broadly, absolutely are there. But you're seeing the industry, I think, as the pressures mount to be more sustainable, and particularly around water and carbon targets, they're more willing to hear this. So I think the interface is excitingly expansive in terms of academic industry research partnership.
Super. And I'd like to segue all of that because I was taken with one of Carlos's points around, and I think Sasha also had one of these, which is that if you're fixing, or sorry, if you're addressing more than one problem with an initiative, that always has a doubling in value or an increase and more likelihood of success. So Carlos, the work around, I was particularly interested in the cementation of tailings for stability, coupled with the other improvements there. If you've got I'm hoping that Justin will give us a few more minutes. And if you could just quickly expand on that, if there's anything there.
Right. So it is a natural consequence of the process of the reaction with the CO2. So we see it happening in mines, for example. Sasha documented in the Australian Mount Keith, these reactions with very reactive tailings that form these cements. With the microbes, the advantage is that in some cases with carbon sequestration, we're looking at a point source of CO2. Also, we need to capture that CO2, we inject into tailings. With the microbes generating CO2, we are replacing that process. So if we don't have a point source to use for carbon sequestration, we can use the power of microbes to accelerate those reactions and try to cement the tailings. So that's the concept behind our approach to cementation using natural processes.
So this is I guess an area in which a young professional just launching their career or considering launching their career. Yeah, I would.
Yeah, absolutely. I think
Yes.
with the dynamics of the carbon markets now and the need for these negative emission technologies, there are skills and there knowledge that is needed to fulfill with the companies or even integrate environmental departments in mining industry and explore these solutions. Yeah, there is a need to understand better these processes. Absolutely, and there's a future for it, at least until 2050, and then if we burn.
Yes, that's right. Well, the point I suspect is that if you're really concerned about that climate change or any of the environmental issues, the mining industry is a viable option where you can explore these things and not only tackle that problem, but to assist in the generation of metals which are vital for this energy transition that we're currently into.
Full breadth of this, I think, is truly inspiring for students for a couple of reasons as we say goodbye to this panel. It's just something they can latch on to. It's something that is progressive. It fits with, the ideas and values of this generation of doing things in this vein, to use a mining term. And I hope that there's a student out there that hears that and says, I'm going to study this. I want a job there, because if I was starting again, that's the kind of thing that I would jump at, and I'm not in the industry. So
and we need you and we want you.
Yeah, well, maybe I'm going to have to switch because that just sounds remarkable. So thank you so much for the session. And as we welcome in our new ones, we'll say goodbye to you and another thanks. And I hope you have a rest of your day, whatever time it is in your time zone. So thank you very much.